I'm Samantha.
I'm Claire.
And I'm Emily.
And this is our Signals and Systems final project, in which we filtered and visualized sound using the fast Fourier transform. So first we decided to do a bit of research on the fast Fourier transform. Essentially, it's a faster way of computing the discrete Fourier transform. We researched the Cooley-Tukey algorithm of the fast Fourier transform because that's the algorithm that NumPy uses, and we use the NumPy library when writing our script. So basically, this algorithm reduces the number of computations that need to be performed. The traditional discrete Fourier transform requires n² computations, whereas the Cooley-Tukey algorithm requires n log n computations, where n is the number of elements you have in your data set. And this works by breaking the data set up recursively, so there are fewer computations to perform. And by recursively breaking down the data set, you can asymptotically approach the n log n barrier. And so here is an example of how the data set might be broken up. So initially, you may have a signal of 16 points. You break that signal down into 2 smaller signals of 8 points each, and then into 4 signals of 4 points each, and so on and so forth. And each time you break the signal down, you are dividing the number of computations you need to perform by 2. So you are performing n² computations on each of these signals, because performing this computation is like taking an n by n matrix and multiplying it by a 1 by n vector, resulting in n² computations. So for the first signal, you might have 16 times 16 computations. But in the next, after you divide the signal up into 2 8-point signals, you will have 2 times 8 times 8 computations to perform. That's a factor of 2 less than the original. And so if you keep dividing the data set up, you are continually dividing the number of computations you have to perform up by 2. And so you approach n log n as you continue to do so. So for our project, we wrote a Python script to animate the frequency content of a WAV file. We first took the sound file and extracted its data, filtered it, and broke the data up into 0.1 second increments. On each of these 0.1 second increments, we performed frequency analysis and plotted the results of that frequency analysis into an image file. We made a movie file out of all of these images and then added the original sound to that movie file so that you could visualize how the frequency content of that sound changed over time.
In order to do this, we used 3 Python libraries, SciPy, NumPy, and Matplotlib. SciPy was used to extract data from WAV files into something that NumPy could process. NumPy was used to perform the FFT, as well as to convolve filters with the audio data, and Matplotlib was used to plot the results. mencoder was used with Python wrapper in order to create a video of the plotted results, as well as to superimpose the audio. So here we have a simple diagram of our code. As you can see, wrapper.py unpacks WAV files into NumPy arrays and applies any desired filters. The data is passed to getFrequencies.py, which divides the data into 0.1 second bins, and then performs Fourier analysis on each of these bins, saving amplitude, phase, and frequency data. This data is passed to Bodplot, which plots the relevant data, and finally, these plots are made into a video by mencoder through example2.py, which also superimposes the original audio on the created video. So we're going to play a video of one of our first experiments, which was pressing some keys in a piano with no filtering imposed. Try to anyway.
Here it goes.
Alright, so in order to create our filters, we use MATLAB's FIR toolkit. We create a high pass, low pass, band stop, and comb filter. Note that these are not ideal, they have been smoothed. This was done in order to better simulate what you see with a physical filter. These filters were convolved with the audio data, and then the filtered data was analyzed and plotted over the base data. This will be shown later in the presentation.
So here are the idealized graphs for the filters, for 5 different filters. The white area represents attenuated part, and the blue is unaffected. As you can see, low pass filter keeps the frequency that are below certain cutoff frequency, and the high pass filter keeps the frequency contents is higher than the cutoff frequency. Here comes our filter results in a video.
Here goes.
Blue dots are the original file, and the green dots are the filtered one. We apply the high pass filter in this case. Here comes more results. First graph shows the results when we applied high pass filter, and the second graph represents the low results for the low pass filter. In conclusion, we were able to see how frequency content changes over time throughout this project, and we saw how filters affected the frequency content of the actual sound file, and we learned more about why FFT is so important and effective compared to DFT. Thank you.